Okay, how's everyone doing?
Yeah.
Ready to bust your brains open again on another evening?
Yes.
Then you get to recuperate for a few days until Monday again. Okay, we're going to start out with a couple exercises. I know yesterday we ended off with the leap year exercise. I will demo that in a little bit, but first, just to get us in the groove, we're going to start with two exercises. And I'm going to send them to you right now on Slack. And please Slack your results back to me. So here we are. So the exercise is to print out all numbers from 200 to 300. So 200, 201, 202, all the way up to 300. Okay, so let's go through this exercise. So we're printing out all numbers from 200 to 300. So if we think about it, that means we need a loop that's going to run about 100 times, really 101 times, because 200 to 300 is 101 numbers, which honestly is something I would miss myself until I run it and I see I'm missing a number. But yeah, that's the good thing about coding is like it's very easy to correct your mistakes. Okay, so let's do, I'll just call it number. We're going to start it out at 200, and we're going to make 101 times do loop. I'm going to close it out. Again, this is a really useful technique. As soon as I create my loop, I end it before I fill in the code in the middle. Because if I start writing the code that goes in the loop, it's very easy to forget the end at the end. And even though that's not a big deal, the computer will tell me that I missed the end, but we may as well beat the computer to the punch. Okay, so I'm going to print out the number. Let's just see what happens if we print out the number without doing anything else. We see that we get the number 200 101 times. Now, obviously, we want 200 up to 300. So in the loop, we're also going to increase number by 1. And that gives us all numbers from 200 to 300. Any questions about that? Okay. I mean, to some of you, this might seem to be simple, but what's cool is that probably by yesterday it wasn't so simple, right? So the fact you could probably see yourselves progressing here. That things that were complicated yesterday are simpler today. And just keep that in mind because we're going to have really hard things today. But just know that, maybe not tomorrow, but it's some time from now, the tough stuff we're going to do today is going to become easier over time with practice. So let's just do one other quick exercise. I'm going to Slack it to you as well in general. It's another one in which you write code. This exercise is to print out all numbers from 1 to 100, but any even number, that is a number that's divisible by 2, should be doubled. So if you get up to the number 10, instead of printing the number 10, you should be printing 20. Does that make sense? Yeah, so I Slacked it to you for reference. But yeah, print out all numbers from 1 to 100, except that every even number, you should print out the doubled version of that number. So when you get up to, let's say, like 8, that should be 16, and 10 should be 20, 20 should be 40. I actually want to, as part of demoing this exercise, I want to teach a new framework about how to use the various tools we have to put them together to solve various problems. So that's not necessarily something that's really teachable. It's something, like I said, comes with practice. Because you all know how to read code now. You all know how to read the code flow. If I give you even complex code, you're able to process it yourself and predict what will happen successfully. But figuring out how to use these different tools, like if statements and loops and variables, to solve different problems takes practice. However, it did occur to me, putting more thought into it over the past 24 hours, that there is at least a framework I can give you to help you to start thinking about these things. And that is specifically how to break down a complex problem into its smaller parts. And then, once you have these various smaller parts, solving each of the smaller parts, and then seeing if you can put that together. Again, still easier said than done. But in this, so here's, I'm going to post up the exercise instructions here. So our exercise is to print out all numbers from 1 to 100, but any even number should be doubled. For example, if you were to print 10, it should be printed as 20. So if I wanted to break this down into sub-problems, into simpler parts, how would I go about that? So one, I'm going to use comments here to identify all the simple parts that I think are part of this complex problem. So simple problem number 1 would be to print out all numbers from 1 to 100. That's something that we're decently good at, as you proved from the previous exercise. Right? You're able to do even more complex. Right? You could go from 200 to 300, which takes a little more thought than 1 to 100. So that's a simple problem. What would another simple problem that's contained within this larger problem be? Doubling even numbers, or if I were to break it down further, I'd say doubling a number. Right? How do I take a number and double it? So simple problem number 2 is double a number. What's simple problem number 3? And the way it says, how do I identify even numbers? Right? Identifying which numbers are even. Now here, this is a complex problem that contains all 3 of these simple problems. And even the most professional, experienced developers don't necessarily look at this complex problem and immediately think of a brilliant solution of how it all ties together. What all developers do is they break it down. They don't necessarily use this framework and write out comments to themselves this way. They do it more naturally because they have more experience. But I think this is something we all could do, which is let's identify the simple things and then see, can we solve each of those independently? And then see if we can tie it together. So I'm going to solve each of the simple problems independently. So here's my solution for simple problem number 1. Number equals 1, 100 times do, print number, number equals number plus 1, end. We're all good with that one, right? That one? Yeah. Okay. Cool. I'm going to now solve problem number 2. Double a number. So I'm just going to make up a new number here. I can reuse the number variable if I want. I'll override it. Number equals 10. How do I double that? Number times 2. So I'll just test it out. Number times 2. So after I have my 1 to 100, we see we get 40 because we doubled the 20 into 40. Any questions about that? Okay. Simple problem number 3, identifying which numbers are even. So number is 2. Or I'll just say, I don't know, 10. How do I identify if a number is even?
Percent sign.
Yeah, that percent side, right? So if number, when I divide it by 2, I get a remainder of 0. That's a very fancy way of saying if the number is even. Then print, I don't know, let's print the number. And I get 10. I'll even throw an else, print 1,000, 10,000. And 10,000 does not print because number is indeed even. So I've taken the complex problem and broken it down into 3 simpler problems, and I've just solved the 3 simple problems. Now obviously when bringing this all together to solve the complex problem, I can't just randomly mix my 3 code samples together and hope it works. We have to do it with some forethought. But I would say we've already solved perhaps the most, the brunt of the problem, right? We've solved every little part of it. Now we just need to put it together. So this is the framework that I want to introduce to you when solving these complex problems, is first identify through comments what are the simple problems, and then solve each of the simple problems, and then come back to the big problem. I think it's just an easier way to think about it. Does that make sense, that framework? Let's try it. It's my first time I just came up with it. We'll see if it flies. Okay, so now going back to our exercise, we want to print out all numbers from 1 to 100. So I'm going to steal this code. It seems like a good little snippet. And any even number should be doubled. So we have our if number. This is where we identify. Well, so this sentence of double any even number really contains my simple problems 2 and 3, right? We're doubling any even number, so we have to first identify which numbers are even and then double them. So I'm stealing this line of code to identify which numbers are even. If that number is even, then I'm going to double it. So I'm going to steal my answer from problem number 2.
I have a key question that I was really having a hard time following. So
yeah.
This makes sense once we print number asterisk 2, right? And that's going to yield us our double numbers, our double even numbers.
Yeah.
I wrote down, and what was not working was I had an if-else statement, or it was an if number percent sign 2, whatever, remainder 0.
Yeah.
Right? Then it was number asterisk 2,
and
then print number, else, then print number and number. Like, basically, I just split the print function and the number doubling number.
So let me come right back to that.
Okay, because it was not working at all.
Yeah, let me come back to that. Let me first finish this, and then I'll come back to your version. So if the number is divisible by 2, then I'm going to print the number times 2. I'm going to print the doubled version of that number. Else, if it's not divisible by 2, I'm just going to print the number as is. And when running this code, I don't really want to delete these. There's a cool little trick. If you highlight a bunch of lines of code and you do command /, and in Windows, I don't know if this works, maybe it's control /, you'll let me know. It automatically puts a comma in front of it.
Do you have to highlight it, or do you just have to be on that line?
Well, if you're just doing an individual line, you can be on that line, but if I want to do multiple lines at once, I have to highlight them. Any Windows users, does that work for you? Yeah. It's control /? Okay, cool. A little pro tip. Okay, so now when I run this, it seems to work, because 1, 4, 3, 8, 5, 12, yeah, it looks good. Looking at this, this is a complicated structure, right? But do you see how I built up to it? I broke it down into first identified the simple problems, solved the simple problems, and then try to piece it together. I'd say of all this, the piecing together is still the most complex part. Like, how do I piece it together? But again, I didn't do it haphazardly, but through logic and trial and error and little luck, you can piece it together. So Ethan, your question was, in your version, you had,
I basically took out...
You said number times 2?
Right, and then print number. Right?
Yeah.
I didn't like
that. Does not work.
Mine worked like the way I...
So delete that, yes, there you go, okay.
So
Summing that,
yeah.
It just does, well, you'll see what it does. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9. It just keeps...
Yeah, so...
Don't break up the statement, so P number times 2. Let's solve that problem.
Right.
Yeah, so this is a great question. So the reason why this doesn't work, Ethan, is because when you say number times 2, you're not actually doubling the number. To double the number, you'd have to say number now equals number times 2. But when you just say number times 2, you're just telling Ruby, process the doubled version of this number. But you're never taking that and saying that's what number should now be.
Okay.
So if another version of this, and you actually don't want to do this, because
Right,
then
the
it's going to mess up.
doubles, yes.
Yeah, but another version of this would be, let's say x equals number times 2, print x, that would work.
Oh, yeah.
But just, so the trick here is, you have every expression in Ruby, if you want to save it somewhere, it has to be tied to some variable.
Mm-hmm.
But just saying number times 2, so let's say the number is 10. What Ruby thinks in its head, Ruby thinks 20. But it doesn't do anything with the 20. It just thinks 20. It's weird. Does that make sense? Sort of? Wait, I just make sure I get that.
I mean, yeah, yes, sort of.
Yeah, so Ruby, I mean, I never really dialed this piece in. What happens, here, I'm just gonna, I don't want to go far off the deep end, but what happens if I type in 10 and run this program? What will happen? Nothing. But will I get an error? I won't get an error. Ruby just says 10. Okay, 10. It's cool. 10. If I say 10 times 2, Ruby thinks in its head 20. It doesn't do anything with that. So it is possible to say something in Ruby just to get Ruby to think about something, but it won't be useful.
Right.
So when we say this number times 2, that's what we're doing. We're getting Ruby to think about the doubled version of the number, but if we don't print it and we don't assign it to a variable, Ruby thinks it, but then doesn't do anything with it. That's basically the point. Yeah.
So I did it like that, but I just made it a single if statement that if it's divisible by 2, p x times 2.
So
Will that mess me up later?
So walk me through what you have.
So I did 100 times do px, x equals x plus 1. If x is divisible by 2, p x times 2, and end.
Can you actually, you already did Slack me. Let me grab no, I got it. Let me grab your code. Okay. Here we go. I have it up here.
Do you? Okay.
Yeah. Does it work before?
It does. It works.
Oh, okay.
But will having like px times 2 mess me up later, or does it not matter because I ended it?
So let me see. Let me walk through this myself. So Cassandra's version is 100 times do print x, increase x by 1. If x is divisible by 2, then print the double version.
And it works.
Well, so it works, but there's one, it's not exactly true to the letter of the exercise, because what you end up having is, for the even numbers, you're printing its doubled version and the even number. And in my exercise, at least my intention was only print the doubled version.
Sure, not both.
Not both, exactly. So your version ends up printing both, because it first prints the original and then the doubled version if it is an even number.
And then it's looping and doing the plus 1. Okay.
Yeah. Or did you have a further question about this? Or did
No,
I?
I just
Okay.
didn't. I
Was wondering if there's. Okay, yeah.
So you like see the doubles and you're just like, oh, it worked. That's cool. So.
Yeah. It's hard to, yeah. If Ruby doesn't give you an error message, it's really hard to spot bugs.
Mm-hmm.
Like the example I had the other day of where you can buy things on credit without using up your credit. I mean, there were no errors, but it's a logical problem. Okay. Cool. Yeah, I'm going to switch around what I had in mind to do at this point. I want to give you an exercise where I want you, I'm going to give you a coding problem, and I did give it to some of you as a bonus problem yesterday, but you'll all be able to do this today. I'm going to give you an exercise in which I don't want you to write any code. I just want you to identify the simple problems. And I don't even want you, yeah, actually I do solve the simple problems. So I'm going to give you an exercise, identify the simple problems, use comments like I did to identify what are the simple problems, and solve the simple problems. But don't try to, I mean, if you want to try, you could, but Slack me your answer even before you try to piece it all together. Basically, I want to train you just in this framework of how to identify the simple problems and solve them. That's all I want from this exercise, because this is a hard one. But solving the simple problems is not nearly as hard. Cool? So sorry, I'm just okay, so in this exercise, like I said, you don't have to write the code. And this is not an example I gave to any of you before. I stand corrected. So here's the problem. Print out all the numbers 1 through 100, and if the number is divisible by 3, print -3. If it's divisible by 5, print -5, meaning instead of the number itself. And if it's divisible by 15, which actually means it's divisible by 3 and 5, print -15. So basically, we want to print out 1, 2, -3, 4, -5, -3, 7, 8, -3, -5. But like 15 and 30 and 45, you'll say -15 instead of those. Again, I don't want the whole solution yet. I just want you to slack me how you broke it down into simpler problems and the solution to each of the simpler problems. So I'm going to put this problem up. Okay, so we have 1 through 100. And if the number is divisible by 3, print -3, divisible by 5, print -5, divisible by 15, print -15. Who wants to, I've seen most of you have submitted stuff, so someone could just shout out, what would you say is simple problem number 1? Yeah, I think you're saying the same thing. Which is, it's printing out 1 through 100, right? And to do that, number equals 1, 100 times do, and print number. I feel like you could do this in our sleep now, right? Number equals number plus 1. Cool. Sweet. So what is simple problem number 2?
Identifying every number divisible by 3.
Okay, identify numbers divisible by 3.
And then printing -3. I think they're basically tied.
Yeah, sure. Printing -3 is a very simple problem, but yeah, we may as well break it down.
I had trouble with last time, so.
Okay, there you go. So yeah, I could break it down like that. So let's make it 2 problems, right? So how do we solve problem number 2? How do we identify numbers divisible by 3? We basically say if number
percent 3 equals 0.
Right. And that code won't run without yeah, I guess it'll run. And for this, we just print -3, right? Okay. Going forward, I'm not going to make a problem out of -5, -15. If we can print -3, we can print the other negatives. So what would you say simple problem? Honestly, we pretty much the same. These are the problems, right? It's just as easy to see if a number is divisible by 5. It's just as easy to see if a number is divisible by 15. We just replace the number 3 with whatever number we want.
The only other case you might argue is separate problem cases, which is like simple problem 4, which is identifying numbers every number is divisible by 15. Because
Okay.
It needs to be, because it's like a case that 1 and 2, it needs where the number needs to be 3 and 5.
Yes, but at this level,
Exception case. Yes, that's true.
but at this level, we're bringing on to simple problems. We don't have to worry about that.
Okay.
You're right. There is going to be a tricky part, and I saw some of you struggle with this. When we put it all together, there is a tricky part to this. But I would say we've identified the simple problems and solved them. So nice job. So now, I know some of you have done this, so I apologize if you're just going to twiddle your thumbs, but now the next exercise is to solve the big picture, which is the original exercise. So if you can go ahead and work on the big picture problem, basically solving this exercise for real, and then Slack me your results. Yeah. So again, our problem here, I'm going to get rid of this for now. Actually, no, I'm not. No, I'm not. So our problem, well, I don't have to restate the problem. You know the problem, right? We have to get 1 through 100. Anything that's divisible by 3, we say -3. Anything that's divisible by 5, -5. If it's divisible by 15, then we say -15. Instead of -3, -5, that's the tricky part. Anything that's divisible by 15 is also divisible by 3 and divisible by 5. So let's start piecing. So we've already broken this up into simple problems and solved the simple problems. So let's start piecing it together. So this is like a good place to start, right? Printing out 1 through 100. That's sort of like our framework. So we'll just keep that as is. Okay. Now we know how to identify numbers that are divisible by 3, 5, and 15. We know how to print negative numbers. So we're pretty good here. So I'm going to start putting this in here. So if here, if the number is divisible by 3, then we want to print -3. Cool? Let's just see what happens. So we get 1, 2, 3, -3, 4, 5, 6, -3. Now we want to replace 3 and 6 with -3. We don't want to also print that number. So I'm going to put this p number in as part of an else to make it that we do either one or the other. So if it's divisible by 3, print -3. Otherwise, print the actual number. So we're making headway, right? 1, 2, -3, 4, 5, -3. Cool. So we're most of the way there. Now let's solve for the -5 piece. So if it's divisible by 3, print -3. So let's use an else if to make another fork in this road. Else if the number is divisible by 5, then print -5. So 1, 2, -3, 4, -5, -3. Cool, cool, cool. Okay, this is the part where it gets a little trickier, and I think this is. I think everyone had to sort of struggle with this. Even if you ended up solving it, this was the tricky part. Else if the number is divisible by 15, print -15. Right? That makes sense in theory, right? If it's divisible by 3, print -3. Also, if it's divisible by 5, print -5. Also, if it's divisible by 15, print -15. However, we see that it didn't quite work because when we get to 15, it prints -3, right? And this was sort of like the big question, like how do we deal with this? So one thing this highlights is that even when you do solve all the simpler problems, it's still not necessarily easy to put it all together. But it certainly helps, right? We're 99% of the way there. We're really, really close. So I would say the easiest way, now some of you started coming up with clever solutions around this, but I don't think we have to get overly clever. I think the way well, I know what some of you have already done, so I know what you're going to say. The easiest way to let's identify why is this happening? Okay, so perhaps this is something else we can throw into our framework. When we do piece it all together, and the code doesn't run exactly how we thought it would, do we know why that's happening? So let's walk through the code and see why does it print -3 where we wanted it to say -15. So let's be Ruby. Let's imagine that we're up to number being 15, right? Starts at 1, but let's say it's 15. So what does Ruby do? It says if the number is divisible by 3, print -3. Is 15 divisible by -3? It is. So it prints -3. And since when you have a bunch of conditions in one if-else structure, remember, you only choose one of the forks, right? As soon as we choose that first fork, Ruby does it, and then it skips over the rest of the whole conditional. Because that's the rule of ifs. If you have a bunch of ifs in one structure, you can only choose one of them. It's like a multiple choice question. You only get to fill in one box. So that's why it's saying -3 here, because Ruby first encountered this condition. If number is divisible by 3 and 15 is divisible by 3, so it prints -3, and then it just skips right down to line 15 and increases number and moves on. So how do we fix this?
So you want to move the if number is divisible by 15 to the top.
Yeah.
Of the pecking order, flip it with -3 essentially.
Yeah. So if we put the divisible by 15 condition up on top, then we make sure that Ruby hits that one first.
So this led me to a broader question.
Sorry, 1 second. Let me just finish this, and then we'll get to that. So now it does work, because when we deal with 15, it prints -15. If it's anything else, though, like 5 or 3 or 10 or 9, then Ruby gets to move on to the other conditions which we want. This is tricky, but we got it. I think everyone got 99%, except for some of you didn't get this last piece. It's tricky. It's tricky. Ethan, what's your question?
The question I had was like, just because I was thinking comparing it to the leap year problem, I think it's a similar issue where it's basically like, is it smart when you're putting these things together, the simple problems together, to find kind of the case that's the most annoying, which I would say is the 15, and like usually prioritize it, because it's like, it's the most exceptional case, it's probably the most annoying, let's put it at the top of the fork, basically figure, if we don't deal with that, then we're going to be fine the rest of the way down, essentially.
Yeah, perhaps as a general rule, perhaps.
Okay.
I can't say for sure because there's so many different types of coding problems out there. I don't know if that always works, but certainly, like, if any case where Ruby's skipping the condition where you want it to hit, think about reordering the conditions.
Right.
Yeah, Kale.
Well, when I was looking at that, I mean, I know when we broke it up, I could see how we were doing this, but what I was looking at is that, and I know this is more of an advanced thing too, but when you're printing out, you're saying, and if number is divisible by 3, we print 3, and if it's divisible by 5, so I was thinking of the ands. So in one of the micro tests, I did it as if, number module 15 equals 0 equals 0, and
and I didn't teach and here.
Yeah, I know, but I'm just saying, that's how I read that problem. After reading it, like, because I was thinking the and.
That is the problem.
Yeah. So I guess the way I did it the first time was right? Because I did it with and?
Yeah, but you don't need and, because this also works.
Okay. That's fine.
Because of this one little math trick that a number that is divisible by 15 is the equivalent of a number that's divisible by 3 and 5.
Yeah.
So that's a little math trick, which I'm not good at math. I found this trick from someone else.
Okay.
Cool. Any other questions? Okay. I have something really exciting to tell you, which is that this problem is a famous coding interview question called FizzBuzz. So you've either solved or got 99% of the way of solving FizzBuzz, which is probably the world's most famous interview question. So this is a real question that they ask in programming interviews. So although it's useless, this is not code you find in real life, but you do find it in real life in an interview. So I'm not saying that you can all get jobs right now, but you are capable of solving some of the interview questions that people ask. Now, the reason it's called FizzBuzz is because the way this is typically asked in interviews is very, very slightly different from the way I described it. And we're going to sort of just take a sneak peek ahead at another concept we're going to learn about later today or early next week called strings. The way this problem is typically phrased is that instead of printing -15, -5, or -3, the question is, the exercise is that if it's divisible by 3, print the word fizz. And if it's divisible by 5, print the word buzz. And if it's divisible by 15, print the word fizz buzz. And the way we would do that, again, I'm jumping ahead, and you're going to all have lots of questions about strings. Just hold them till we get there. But this is to print a string, use quotes and the words and the letters inside. Again, there's lots of questions, but I'm not going to address them now. Ethan, have you ever heard of FizzBuzz?
Yes, I have heard of FizzBuzz.
So now you could solve FizzBuzz.
Yes. That's cool.
Yeah, so this is the famous FizzBuzz question. Sometimes, the way it's also typically asked, they don't usually tell you it's divisible by 15. What they usually say is, if it's 3, say fizz. If it's divisible by 5, say buzz. If it's divisible by 3 and 5, say FizzBuzz. But this little trick is that if it's divisible by 15, that means it is divisible by 3 and 5. So yeah, this is the famous. You can Google like FizzBuzz and you see everyone talking about FizzBuzz. This is the world's probably most famous interviewing question for programmers. Now they ask more complicated questions too, but this is sort of like the first level. You know, like let's see if you can do this. Now, it's sort of silly that they still ask this, since everyone knows it's the most famous interviewing question. We had a grad he was laughing so hard. We do FizzBuzz in class, and he was just telling me, Jeff, tell me a funny story. I got asked FizzBuzz. I'm like, really? He's like, yeah, but they didn't tell me it was FizzBuzz. They cloaked it. They said, if it's divisible by 3, say apple. If it's divisible by 5, say orange. He's like, I know that's FizzBuzz. Everyone knows FizzBuzz. Anyway, so yeah, congrats on being able to do FizzBuzz. Okay, let's take a break. So let's start up again at 7:30, and I will demo the leap year problem. But I'm going to start with the same framework. Like, let's break it up into the simple problems and then build it up.
Game Boy TI. Even had the Game Boy Color. They have a color one now.
Okay, let's talk about everyone's favorite subject, leap years. Since we did end off with that exercise yesterday, let's just come back to that today. I'm going to go ahead and demo it. So here is the exercise. So we're printing out all leap years from 2000 to 3000. The rules of leap years, unfortunately, are somewhat complex. So leap years are all the years that are divisible by 4. But there are exceptions. If it's divisible by 100, it's not a leap year. But there's an exception to the exception, because it's divisible by 400, then it is a leap year. Yeah. So again, I'm going to just break this down into the simpler problems. So, and you'll help me. So simple problem number 1. What would you say simple problem number 1 is?
Just 2,000 to 3,000 printing out the numbers.
Print out all numbers.
Or at least all 4 years.
Yeah, so there's 2 ways to go here. If I wanted to get really simple, I'd say print out all numbers from 2,000 to 3,000. Which we can solve with this. Year is 2,000. 1,001 times due. And print year equals year plus 1. So we solved printing out all the years. Cool? Simple problem number 2 is basically printing out, like Ethan said, print out all,
Leap years,
I guess only print out, well, I guess it's identify, right? Identify years divisible by 4. Would you say that's a good, simple problem? So if year if the year is divisible by 4. Okay, so we solved that simple problem. And we'll use that same approach for determining if a year is divisible by 100 or 400. I don't have to rewrite those. That's identifying if a year is divisible by a particular number. Are there any other simple problems here? It's just tricky when you put it all together, right? Because there's an exception, and then there's an exception to the exception.
Right.
So that's like conditional nightmare.
Yes. That's why I think again it's like just like find the most difficult, unusual exception, pop it at the top of the fork, basically.
Yeah.
I guess I'm just being trained to do this.
Yeah. So, and the truth is, I'm pretty sure that I saw some of your answers from yesterday, and I think I saw 3 different approaches to this. Not wildly different, but different. So, and if I take what Ethan is saying, that will probably yield us the simplest approach of the ones that I saw. So we can try that. So let's try to piece this all together. So I'm going to just steal this, because that's good code. Now, let me so some of you did this cool trick, which is you did year equals year plus 4. So we actually, some of you did this where we didn't even have to write a conditional, but we still achieved our first piece, which is just printing out all years divisible by 4. Whoa. Well, then you have to do it. You have to do fewer than 2,000 times, right? What is it going to be? 250? So since 2000 is a leap year, then we start from there and then go just increase by 4. So we actually, this was a clever trick of where we didn't actually need an if statement, but still achieved the first puzzle, which is just getting all the basic leap years out. You could do that. We could keep it at 1 and check, if the year is divisible by 4, then print it.
Right.
And then else don't print it. And that achieves the same result.
No, and year percentage for.
Oh, thank you. Thank you. Thank you.
Oh, yeah, there you go.
That achieves the same result. Is one better, worse? The only case I can make for one being better is that the first way I did was faster because we only had to loop 250 times, and here it's loop 1,000 times. So, I mean, you can tell the difference in speed, right? We're talking a second, right? We're shaving off a millisecond, but there is that difference. But I'll keep it this way for now. So yeah, Ethan's strategy is pretty solid here because the hardest ones
are the 400s, right?
Yeah, if you start in these types of problems, if you start with the hardest ones, putting them on top is certainly helpful. So if the year is divisible by 400, then we want to print the year, right? Else if the year is divisible by 100, don't do anything.
Right.
Else if the year is divisible by 4, do print it. Else, if it's any other year, don't print it. And I think that actually solves the...
I think we gotta get rid of the other else.
You're missing the equals.
Oh, thank you. Thank you. I think that does solve...
We can go to 2400 and see if 2400 is there.
2400 is there.
2500 is that there?
Should it be there?
No.
2400 is not there, but 2400 is divisible by 400, so it is there.
Yep.
So it looks right. 3000 isn't there. Is 3000 not a leap year?
No, because it's delivered by it's divisible by 100.
Is 3,000 divisible by 400?
Divisible.
No. Okay, so 3,000 is actually not a leap year. So it's good that we didn't print it. So this is I would say this is probably the easiest solution to read. It's not to say that any other solution out there is wrong, but this is just sort of where I might go, and I saw some of you took this approach. Yeah, this I guess is another example of where like it's pretty easy to solve the simpler problems, and the real trick is putting it together. But still, in any case, you always want to start with solving the simpler problems. Any questions about this? Okay, let's go for one more. Yeah, we're going to try this framework for one more exercise, and then we'll move on to the next new concepts. So here's a tricky exercise. I only want you to put comments identifying what the simpler problems are, and then solve the simpler problems, and slack that to me. If afterwards you want to go ahead and try to solve the big thing, that's fine, but that's not the point of this exercise.
Just comments? Or
just
to break down the comments too?
Just like, I don't have it anymore, do it. Yeah, just like this, where you identify in comments the simple problems, and then you solve the simple problems.
Okay.
So let me slack this to you. I'll also try to describe it. It's a little weird. Using just one loop, print out the numbers 1 up to 100 and then down to 1 again. So 1, 2, 3, 4, 5, 97, 98, 99, 100, 99, 98, down to 1. But just use one loop. So it's tricky. But again, all I'm asking you to do is identify the simple problems, solve the simple problems, and slack that to me. We're actually not going to solve the. I'm going to just demo the answer to the big problem, but I'm not going to have you do that. So this actually should be a pretty quick exercise. Look at this. This problem is very tricky. But at least we can break it down into simpler problems. Okay, so we want to write a program that prints out 1, 2, up to 100, and then down to 1, just using one loop. That's sort of like the big constraint that makes it super hard. So what is simple problem number 1? A loop that does what?
Numbers 1 to 100.
Okay, so print 1 to 100 is one simple problem. That's fair. So let's say number, I feel like I've typed this out 20 times tonight. Number equals 1, 100 times do, print number, number equals number plus 1, end. Right, and that works. What is simple problem number 2? I like that. Print 100 to 1. So number equals 100. 100 times do. Print number. Number equals number minus 1. Yeah. Now really, we've pretty much accomplished the exercise, except for the fact that the exercise says do it in one loop, right? So this is great. Is there a third simple problem that anyone wants to point out? Do it in one loop. That's the complex problem.
So like something like the division, the remainder of the. I was trying to think of a way to stop the clock, so to speak, right? Once you get to 200, it's like something like if the remainder of dividing it by by 100 equals 0, right? That puts it then there like some sort of thing that makes it count up to 100, but it's some sort of like way to prove that it gets to 100 and then forces it to go back down. I mean, I don't know how else to explain what that simple problem is.
Yeah. You're basically describing sort of like the complex problem, right?
Right, that's
yeah.
That's the tricky part.
So, since I already know how I want to approach this problem, it's easier for me to identify a third simple problem here. But I sort of want to, this is sort of where I'm introducing a new concept. It's not entirely new. It's nothing you don't know about programming. It's just sort of another like thing out of my bag of tricks, which is the usage of a brand new variable that we'll make up to keep track of something. So I'm going to make a simple problem number 3, which is keep track of whether we should be going up or down. I'm going to make a variable called up. Just made it up. Up equals 1. So this is, again, sort of really getting into the solution. But the strategy here is that I'm going to make a variable called up. And when it's 1, that indicates we're going to have to tell the code to do this. But that keeps track that, OK, we want to go up right now. If I change up to, let's say, 0, then that means we want to go down. OK? This sort of isn't super helpful until you sort of see where I'm going with it. But that is going to be my strategy. So let me pull this all together, and I think then it'll become clearer. So if you want to do it in one loop, we really need like a loop that's what, like 200 or 199?
Yeah.
Is it 199? So we're going to start with number at 1. I'm going to just steal this. Number is 1, and then we want to do this 199 times. And this part looks good, right? But this, here, I'm going to comment these out. That's what it's called, by the way. Commenting it out is actually like a verb. To comment something is to do this. If we run that, okay, that gets us 1 to 199. We want it to stop at 100 and then go back down. So I'm going to do this. I'm going to start my up variable at 1. Now, just because the computer has no idea what this up variable is, right? I could have named it purple hippo and still accomplish what I want to accomplish. But to me, this is meaningful, right? So up equals 1 means we want to go up. As soon as I want to go down, I'm going to make up into 0. So print number, if up equals 1, then I want to increase the number by 1. Else, meaning up is 0, or really anything else than 1, then I want number to decrease by 1. Okay? Now this, let's just see what happens when we run this. We still get the same result. Why do we still get the same result? Because we've never changed up, right? Up starts out as 1 on line 4, and we keep on saying if up is 1, keep on increasing number by 1.
Right.
But nowhere do we ever get changed up to something other than 1. So we are going to continue going up from 1 to 199. So the key here is, okay, when we get to 100, we want to change up to 0. So I'm going to put another if statement here. It says if number is 100, then we're going to override up and make it 0. Now let's see what happens if we do that. It looks close. So 1, let's see how far we got. 100, yeah. Yeah. Now this, if I threw this code at you and asked you to predict what it would do, you would predict this. The tricky part is figuring out how to build this. And I saw other people actually had a different solution for those of you who tried to solve this. This is sort of the way I would go, but I'm not sure what I'm trying to point out with this, but the main thing is a lot of times you're going to need to pull new variables out of your hat to keep track of things. I guess that's sort of a vague takeaway, but I want to show you this example because that is a very common tactic, very common trick is like, I want to keep track of some sort of thing that's going on, and if I have to make up a new variable to do so, so be it. Even though the exercise didn't tell me to do that, it just told me to keep track of the number, but yeah, if I needed to keep track of whether I'm going up or down, I might need a new variable to keep track of that.
Definitely simpler than what I did.
I didn't get a chance to see what you did.
It's something kind of similar in a sense like that, but
yeah, this is certainly not the only solution. This is just where I would go. Again, I can't, it's impossible to teach how to be clever. The way I can do this is because I've seen so much of this before and done so much of this before that it comes natural. And like I keep on saying, the more you practice, the more this will come natural to you. But the least we can do is break things up into simple problems and then try to put it together and keep on practicing. Yeah?
Will you just slack this?
Yeah, absolutely. So let me save this. And I'm slacking this to general so you have it as reference. And again, it's not the only answer. Cassandra, you want to say something?
Yeah, I copied what you have up here, and it's
Not working for you?
working.
I'll check it out later.
Yeah.
Keep it on. Keep your tab
Sure.
open. Yeah. Okay. Any other questions about this? Okay. Continuing this tactic, I have a new exercise for you, but this one is just a prediction. Okay. I'm not asking you to write code, but don't run the code either. I'm going to slack to you a code snippet, and I want you to predict what it will do. So don't run it. So I just slacked that to you, and I'll put it up here as well. And I'll just, I guess just slack me when you're done. You don't have to slack me anything. Just slack me when you're done so I know when to move on. We will walk through this together. This is a pretty tedious problem, I have to admit. So let's predict what will happen. We've got number and jump. What does jump basically represent? It's sort of like this changing number that changes like the increments that we change the number by, right? So number starts out as 3, jump starts out as 3. So let's walk through it. I'm going to use a comment here to keep track at all times of what number is. So number right now is 3. On line 7, 10 times do. I'm also going to keep track of, yeah, which number we're up to, which time through the loop. So we're up to loop 1. Okay, here we go. If number is less than 10, is number less than 10?
Yes.
So number is now what?
6.
Number is now 6. And it looks like we're also going to need to keep track of what jump is, right? Jump is going to be 2. Okay, we're done with that loop. We end up printing the number, right? So we're going to
print 6.
Yeah, we're going to print 6. I'll just keep, okay, cool. Well, loop number 2, number is 6, so is number less than 10?
Yep.
So what is number now?
8.
8, great. And jump is still going to be 2, and we print 8. Okay, and now we're up to loop number 3. So is number less than 10?
Yes.
Number is now 10. Jump is still 2. We print 10. And now we're up to the 4th round of the loop. Is number less than 10?
No.
Else if is number greater than 10?
No.
So we get to the else, right? That if none of the above. So number is now 20. And jump is now 3. And we print 20. We're up to round 5 of the loop. Is number less than 10?
Yeah. No, sorry.
No. Else if number is greater than 10.
Yeah.
So number is now 17. And jump is now 1. And we print 17. And now we're up to round 6. Am I going too fast? Is this making sense? Okay. So number 17. Is number less than 10?
No.
Is number greater than 10?
Yes.
Number is now
16.
17 minus 1. That would be 16. So number is 16. Jump is 1. We print 16. And we're up to loop 7. Okay. Is number less than 10? No. Is it greater than 10? Yes. So number is going to be 15. Ruby does this all as well, by the way. Ruby keeps track just like we are. And then jump is still 1. And we're up to round 8. If number is less than 10, number is 15. So is number greater than 10? We reduce it by 1. So number is 14. Jump is 1. We print 14. And it's going to be 13 and 12.
12, yeah.
Just following that pattern.
Yeah.
Is our prediction right? Thank goodness. I don't have to go through that again. Any questions about that? Okay. Let's move on to perhaps the most brain-bending concept of this entire week, if not the entire 2-week course. So 8:09 p.m. is a great time to introduce a brain-bending concept. So here we go. Okay. Remember how we had nested if statements? That was an if statement within another if statement. We talked about the different levels, level 1 ifs, level 2 ifs, level 3 ifs, till infinity. You could also put loops inside of loops, which are called nested loops. And those get tricky, however, they're very predictable once you know how Ruby processes them. So here is such an example. We have an outer loop. We call it a level 1 loop. No, I made up the term level 1, but think of it as a level 1 loop. Most people call it an outer loop. And we print 5. So we're going to end up printing 5 times, right? But we also now introduce a loop in here. Now remember how Ruby knew when an if statement was within another if statement? That's every time Ruby hits an if before it hit an end that concluded that if, that means we move in a level. Here as well, if I remove the indentation, Ruby would still know that this loop is an inner loop because we had this outer loop here, we never hit the end yet, and we're already introducing another loop. That means this loop becomes a level 2 loop, which means it's inside the first loop. So I'm going to give you a couple options, and there's no way to know. It's completely arbitrary how the designers of Ruby made this. But here are the options of how Ruby processes this. One way is that Ruby will print 5 times, and then print 10 times. Another alternative is that Ruby processes 5, and then 10 times, and then go back up to do 5, and then 10 another time, and then 5, and then 10 another time. Is there a third possible alternative of how Ruby processes this?
I think it's going to alternate 5 and 10.
5, 10, 5, 10.
10.
Oh, so Cassandra's presenting an awesome third alternative, which is 5, 10, 5, 10, 5, 10, 5, 10, 5, 10. We sort of exhausted the outer loop of 5, so now we just go 10 the rest of the way, a bunch of 10s, 5 more 10s. So let's just see. It is the middle alternative, okay? And so Ruby works like this. And so do all programming languages that have nested loops. I'm going to use comments to indicate this. So Ruby hits this line first, then this line. I'm going to skip the blank line. 3, sorry, that's not a 3. 3, 4, 5. Ruby always processes an inner loop fully. before going back to the next round of the outer loop. That is the golden rule of nested loops. And you just have to write that on your forehead. Writing things on your forehead is the worst thing, because then you have to look in a mirror to find it, and then it's backwards.
Isn't that useful?
Yeah. So write on your hand, maybe. It always processes inner loops fully before going back to the next round of the outer loop. So that means Ruby's going to go 6, 7, 8. Oh, this is tedious to write all this. 9, 10, 11. You get the idea, right? 13. I'll always finish it. 15, 16, 17, 18, 19. Tell me when I hit 10. What is that, 6? Ruby does this a lot faster than I do. Thank goodness. 31, 32. What do I have, 2? That was 10?
Yeah.
Sweet, okay. And then 3, 4, and then, sorry, not far, I'm at 33, sorry. 33, 34, and then 35, 36. I'm not going to, et cetera, et cetera, et cetera. Is that nuts? That's just how it is. In my head, I'm so used to this that to me this seems logical, but I realize it's sort of arbitrary. But the way I look at it is like, okay, Ruby says, outer loop, 5 times do the following. For 5 times, I want you to do a loop 10 times.
Yeah.
Right, so in time number 1, we're doing a loop of 10 times. Time number 2, we're doing an inner loop of 10 times. Does that make sense? Or just remember the rule. Ruby always processes the inner loop before it goes back to the next round of the outer loop.
Would you say a useful way of remembering it too would be kind of thinking of a say 5 times do. Now unless you see a dot times do for a function, you could think of it as just like 5 times say 1 for P5. And then that's not talking about the order you'll see, but just like the total number of times you would see that function be ran. And for the 10 times do, just think of it as 5 times 10. So in other words, that print 10 is going to be ran a total of 50 times. So
right. Meaning just like, if I understand you correctly, just like this runs 5 times, so this thing runs 5 times. And as part of each round of the loop, we run that inner loop 10 times. Then we go back up. I always want like an animation for this, like some sort of like wheels or something, where like the outer wheel goes around once,
Gears.
the inner wheel, the inner gear goes around like 10 quick times. Then the outer wheel goes back another big time, and the inner wheel goes like another quick 10 times. Like a what?
Like a clock.
Like a clock. I have no idea how clocks works, but it sounds good. I believe you. Yeah, so it is sort of mind-bendy. Okay, so here's an exercise. It's a prediction exercise. Predict what will happen in this code snippet. So don't run it. But just predict what will happen, and just slack me when you're done so I know when to move on. Booyah starts out as 0, right? Then we start the outer loop, 2 times do. So I'm going to keep track of which round of the loop we're up to. Okay, and I'm going to keep track of what Booyah is. So it's 0, and we're at loop round 1, right? So Booyah increases by 1, right, on line 10. And then we start the inner loop. So 2 times, do I have to need another tracker for my inner loop?
Probably.
Outer loop, round 1. Inner loop, round 1. So, Booyah is Booyah plus 2, so that makes Booyah 3. We now start inner loop round 2. Booyah increases by 2, so Booyah is now 5. We reach the end of the inner loop, and now we go back up to the next round of the outer loop. So now outer loop round 2. Let's reset that inner loop. It's going to be round 1. So Booyah is 5 as of this point.
6.
So Booyah becomes 6 as of line 11. Then we start the inner loop. Inner loop round 1, Booyah becomes 8. And now we're up to round 2 of the inner loop, and Booyah becomes 10. We conclude the inner loop. We conclude the outer loop. We don't go back because we only had to run it 2 times, and we did both times. So Booyah should be 10, and it is. Any questions about that? Now, did you know that you can have inner loops inside inner loops inside inner loops inside inner loops inside inner loops? You should never write code like that, but you can have it. It works. So don't kill me. I'm going to give you an exercise that has 3 nested loops. So that's a loop inside a loop inside a loop. It's very similar to this past exercise. Again, all I want you to do is predict what will happen. And then we'll take a quick break and infiltrate Kazakhstan once again. So here is, that's not what I meant to send you. There, so just predict what will happen. Let's walk through this. The way this is going to work, we have to do the same thing as before, where we need to keep track of everything. Yeah, so here I can't refer to it anymore as an outer loop and an inner loop because there's 3 of them. So I could call them, I don't know, outer, middle, inner. I guess I'll go with that, right? So we need to keep track of outer loop. It's going to start at 1. Middle loop. It's going to start at 1. Inner loop. It's going to start at 1. And of course, we have to keep track of Booyah. So, okay. Booyah is 0 before we begin any loop. So far, so good? 2 times do. Line 12, Booyah is now increased by 1. Whoops. So we increase to 1. We then start the middle loop, where Booyah first gets increased by 2. So it's now 3. And now we start the inner loop. So let's one at a time. So we do inner loop once. Round 1 increases it by 3, making it 6. Now we're up to round 2 of the inner loop. Because the innermost loop has to complete its rounds first before its containing loop goes back to its next round. So we now start this again, and Booyah increases by another 3, making Booyah 9. So we've completed round 2 of the inner loop. We now go back to the middle loop. So middle loop starts its round 2, and we'll reset the inner loop to round 1. So the middle loop starts, Booyah increases by 2, making it 11. We then start the inner loop. Booyah increases by 3, making it 14. We then start round 2 of inner loop. So now we're up to middle loop 2, inner loop 2. Booyah increases by 3, making it 17. And then we've completed our inner loop. We've completed the middle loop. So now we go back up to the outer loops round 2. Let's reset the middle loop and inner loop to round 1. Is this making sense?
Yeah.
You understand why it's horrible to work with this kind of code, right? Okay, so start over. Round 2 of the outer loop. Booyah increases by 1, so it's 18. We then start the middle loop. Booyah increases by 2, making it 20. We then start the inner loop. Booyah increases by 3, making it 23. we now begin the inner loop's second round. Booyah increases by 3, making it 26. Whew. We now go back up to the middle loop and start round 2. We're going to reset the inner loop to 1. So Booyah increases by 2, making it 28. I'm losing track of things. And the inner loop starts. Booyah increases by 3, making it 31. We now begin inner loop. Round 2, Booyah increases by 3, making it 34. We're done with our inner loop. So the middle loop's also done. The outer loop's also done. So we have successfully exited this entire loop structure to move on to print Booyah, which better be 34, thank goodness. Yeah, so that's 34. Super twisty. But that's, I mean, Ruby goes through the same steps we just did to determine what the result will be. And again, this is 3 nested loops, but you can go to an arbitrary, I mean, just don't, but you could. Any questions about that? Okay, let's take a quick 10-minute break. Come back at 8:46, and we'll infiltrate Kazakhstan for another time. Oh, I had to do that exercise.
Oh, the
Yeah.
Yeah, I had that.
That was hard.
Oh my god, it drove me nuts.
That's funny.
Yeah.
That was good though.
Yeah, but it's when you read assembly, it's like, what?
Yeah. Okay. Everyone's favorite country. Again, here is the link to the QCH website. And I'm going to put it up here. So we actually just hacked another department at the QCH, namely their cyber warfare department. Now, frankly, I don't quite know exactly what cyber warfare refers to. It's sort of this vague thing, but it sounds bad, and it would probably be a good thing if we disabled it. So we hacked the part of their website that has the code for their Department of Cyber Warfare, and that I'm slacking to you as well. Now, I don't know what it means, but it's up to you developers to figure that out for me. Yeah, I think that's all you need to get started. If you have any questions, we're here. Good luck.